Hello Internet! Today we're going to talk about concurrency and streaming and a nice library that actually solves a very interesting problem. So first of all, let's start with the problem statement, which is you've got some data and it needs to be processed. Let's say you've got an LLM that produces some hallucinated words. And it streams these words in chunks, but that's not enough because you're not actually just streaming the output. You'd like to actually apply some processing to each chunk that is generated. So the naive way to do that, let's say that we've got our streaming, which is we started with pure Python async streaming. We need to let's pretend we need to capitalize, then lower the output, and just for good measure, we'd like to filter out any word that is shorter than the 3 characters. So the naive approach would be to stream that with basically just a normal iteration. You'd map over the with you'd have some processing delay. And then you'd filter everything, then you'd capitalize, then you'd lower. And we pretend that each of these processing things is actually taking some indeterminate amount of time. Here we just introduce a delay of 0.02 seconds, sometimes 0.03. And you can pretend that is just networking for an external service that does that for you. So if we try to visualize that, that would look like that. That would look like so. You'd have the initial generation, then you'd need to actually do some processing of the chunk. Let's say as we said, filter. Then we'd need to capitalize, and then we'd need to lower. And that's it. So we've got some kind of chunk that needs to go through all of this pipeline. But we've got a lot of chunks. So the streaming thing would basically go for that chunk by chunk. So this is, as you can see, not very ideal because, well, we have a lot of processing that we can do in parallel because there is no dependency between each of these chunks. So we'd like to actually parallelize stuff. By the way, each of these could have been a little bit shorter or longer, and that would affect how we would how could we actually like pipeline everything. So now that we've got some kind of like image on how things look when we are going for the streaming solution, let's actually run that, and you'd see our results. So as you can see, we are processing our first word all the way through the pipeline. Then we go for the second word. Here the word is too short, and then it's dropped, and then we don't see it anywhere in the pipeline anymore. Then we generate the next one. And then we've got our hallucinations, another word, and everything is just taking a lot of time. And specifically, it takes, let's actually run that with the actual logging. If we run everything, this takes, I think, around 13 seconds. Okay, so 11 seconds. So 11 seconds is not too bad, but also we could do better. Because as we've seen, there's not a lot of dependencies between each of these processes. We actually want to have them independent. So here, AIO-Chan is the library that we throw at this problem for a solution. It's a concurrency library that models how Go and Clojure does some async processing, and specifically it uses channels. So here we are actually, okay, so here let's look at the solution from the channel perspective. So we've got our channel. We just pretend we've got like some kind of concurrency target that we want to hit. As in, we'd like not to parallelize more than 15 tasks at any intersection point between processing steps. You could also tune that and have for each of these processing steps a different amount of concurrency limits, just so you know. And how would that look? So this would allow us to basically, let's now take that into another timeline. So now that we've got that, we could actually start the processing of each step as soon as possible. So we could actually start like so, and then run another chunk. And each of these can be actually processed in parallel as long as you've got enough resources, and as long as we've got enough cores and the concurrency limit is not actually pushing us. So each of these, as we can see, is now pipelined and stacked up much better on the timeline. And if we try to duplicate that, we should be able to actually... okay, let's pretend we've got a concurrency limit of 4. So what would happen once we hit the 4th task and we are now locked and we don't have enough capacity to run the next task? It would wait to run here. And that way we've got our another thing. So that way we've got basically almost perfect pipelining. Of course, this is too ideal what I'm drawing right now, because nothing actually takes like a truly perfect and predictable amount of time. But this is basically what we are aspiring to reach, which is keeping our computers busy and our resources busy, and not locking anything that doesn't need to be locked. And here, as you can see, there is a dead span of space between the between the 4th chunk and the 5th chunk of actual time that is now the chunk is just waiting. And this is why increasing the concurrency on your of your system is actually a good thing, because that means you can basically process more chunks independently. Going back to how it looks, so we've got our concurrency limits. We just arbitrarily chose 15. We can go for 5 just for the demonstration purposes. We've got our generation, which now it's not yielding as an async generator, but it is putting the elements onto the channel. Once we've got our elements onto the channel, we are scheduling the channel closure once we are done with generating all of our inputs. And then we actually look at the processing pipeline. So we start with the channel, we pipe in the processing delay, then we drop the short words. You can pretend these are basically just one processing chunk that resolves in some kind of solution. Like this is basically an async filter solution. We've got another pipelining through the capitalization, then lowering, then another blocking operation. If we run the new code instead of the old code, we actually get a faster pipeline, like significantly faster. We are now topping at, we are finishing at 2.4 seconds, which is a lot faster, and we are doing the same amount of work in both, just pipelined a lot better. And that's it. This is what I wanted to show you today. I hope that seemed useful. The package name is AIO-chan. It is a very useful package, and I will probably use it in some projects. See you all in the next video.